talk a little bit about what would I do if I wanted to numerically sort of solve a second order system. And I want to show a little bit about what does the time responses look like in the second order system, because it might be very, very helpful in both of these kind of perspectives thinking about these approaches. So how do we set this up? And so the way that we start off with is that you can actually start off with a low-pass filter. This is a low-pass filter circuit here. For all of this, I'm going to be using the L as 200 millihenries and the capacitance is 125 picofarads. I'm also going to look at a high-pass version of this circuit here, which is actually going to be these diff EQs. You can actually take the circuit, and this would be the differential equation you would get here, where you would say my tau is going to be L times C. Okay, and I'm also then going to get my Q is going to be R divided by the square root of L over C. In this case, that value is going to be 125 or 1.25 kiloohms. When I actually look at the L times C and take the square root of it, that gives me the time constant. That's going to be 0.16 milliseconds. That's also going to give me my corner frequency. And so we're going to have that normalization step. In fact, this is extremely important typically when you're talking about doing these kinds of things numerically, is that you'll typically want to do some sort of normalization step to get where you need to go with these structures. So to start with, like if I'm talking about the low pass structure, I'm going to say I'm going to have a step response of some size, call it X steady state of whatever it's going to step to from 0. So this is just the unit step function. Well, I know that I'm going to start off with an initial condition of everything that happened beforehand is 0 because that's what U of t would be. I know this is going to give me a steady state, so that's what I'm going to get. So it turns out that one way to solve this is then to say, well, imagine that I have this differential equation with X steady state, and then I know that my initial condition is 0. And that's the way I would probably formulate out the mathematical expression there. But the thing that's very useful here is then to also normalize out time. So anytime you're actually, so one is this is very important if you're analyzing differential equations, because you usually want to get the time normalized out, because time, that sort of normalization says, look, I can scale this to any sort of time I need to, and I still get the sort of basic dynamics that I'm looking for. And so I can just scale that one variable. I know what that variable is. I can work with it and proceed. It certainly minimizes the number of other variables I have to look at my dynamics. It's also really important because when you actually then move this into a numerical case, you typically want to normalize that so that way you actually build any of the numerics or the step sizes, normalize to that value. So this is why this typically is very helpful. So you say, great, this is a second order differential equation, but how do you actually put it in a framework you could actually typically solve this? Let's say you're going to put it into a set of differential equation solvers. Well, you typically actually need to get this into a matrix form. And so that usually means that I'm going to do something like, say, like y1 is equal dy dt. And by doing that, I can then reformulate this as a matrix formulation. If you like state variables, this is certainly where this is going, where I have a constant term here. I have a state variable matrix, and I can do this. Now, from here, it's very easy to then put this right-hand side into an ODE solver and say I'm going to just do RK45. I actually generated these graphs in MATLAB, and then I could actually see what that response would look like. I actually put additional offsets so you could see all of them on the same curve. We'll talk about this in a moment. What happens in the high-pass filter case is I start off with an equation that looks something along these lines. Well, here's where it gets more interesting. You're saying, well, I have my input, which is a U of t, but I'm taking the second derivative of it. And you think, that's going to be a problem. Because like, what does that mean formulate? Because if I just take the derivative, the first derivative of x, that's going to give me an impulse function. And the second derivative is like the derivative of an impulse. And you're like, oh, that's an interesting problem. But it's nice because so how do I think about this? Well, the first thing I do know is that after sort of t equals 0, my derivative is 0 and my second derivative is 0. So the nice thing is that this is basically going to give me 0 all the way through. And we'll typically talk about that as sort of like, t0 plus, so just after the 0, and everything past it is basically going to be just 0. So it gives me a very nice matrix formulation. Basically, I don't have to worry about this part, and pretty much everything else kind of comes along for the ride, which is kind of cool, right? Except, what do I do about the beginning? Well, what I do at the beginning is just imagine I took this different ODE, and if I did a multiple different ways to approach this. I can think about this physically as the capacitor is moving much faster than the R and the L, and so that when I move the input voltage, it immediately moves the output voltage by the same amount. And so that means that the step is the same. I could also say, let me look at this in perturbation theory and look at the order of the derivatives in terms of time, scale time towards 0 if I want to be really rigorous about it. What I'm going to find is that that derivative in y and the derivative in x are going to be about the same. Also works. So a couple different ways to talk about it. Again, I love the physical case of talking about the capacitance. The capacitance just can't change fast enough to be able to handle any other dynamics. So the output voltage has to go with the input voltage. That voltage across the capacitor can't change. That seems to be the easy way to approach this. And when you do that, what you find is that not only do you get that really says I got a nice sort of step, but then after that it just sort of converges to 0. So the initial low pass are basically steps, and I put a constant in here so I could see them all in the same plot, use different Qs from 1/8 to 8, and I could see I get a a nice long sort of case because I've got the long time constant that's setting things, the long eigenvalue if you want to go there. Q equal 4, it's actually going it's going twice as fast. Q equals to 1/2 is where I have 2 roots. This is where it's going to be right at where the time constant is. I know the time constant's about it's about a millisecond. So notice about 1 millisecond. After about a millisecond, this is really, the tau is 0.16. So that's about six time constants per millisecond. And about that point, I'm already up, and so I'm in great shape. And notice this is half, and that's half the speed. And so I could say, well, where did this one kind of converge? Well, it's much, much longer. And I know that I'm going to be having a much longer time constant as a result for this one, shorter for this one, and so forth. This sort of little overshoot tells me I'm at about a Q of 1, which is exactly what I'd expect. Q of 2, notice I've got multiple bumps. An interesting rule of thumb is that if I've got the number of bumps I can see very easily, in this case I can see 2, divide that by 2 gives me roughly my Q. So I see roughly 1, 2, 3, 4 pretty easily. That's a Q of 2. 2, 3, 4, 5, 6, 7, 8-ish, about 4, and so on. I'll also notice that the period of this is about a millisecond, which is what I'd expect from 2 pi times 0.16 milliseconds. So it really does tie to that corner frequency is what that oscillation frequencies are. And so I can definitely see this. Similar thing happens on the high frequency side, except that notice it starts there, an initial sort of 2-volt jump because I'm using 2 volts as my XSS in this case, and then it then just sort of comes back into solution. This is then 4, 2, right at the 1 case, and you can see these get progressively larger as I look at these. So it's kind of neat to look at the dynamics, the time dynamics. There's so much richness in the time dynamics and the second order behavior. It's also very cool that you can set these things up, look at its physics, and even set these up. You could numerically compute these so you could actually see what's actually happening throughout.